let's talk about heat pumps, but I want to step back. So I'm going to start with a bit of history. I'm going to then come in and talk about very practical things and focus on those. And then I'm going to move out again to talk about broader issues and wider issues. So hopefully it will satisfy different appetites. So a bit of brief history. So heating in England. I guess we have to go back to Athelstan if we're going to talk about England, aren't we? So since time immemorial, we heated our homes with wood, and that was true in Athelstan's time, right up to about the 1500s when we started running out of wood. And coal, we started using coal to heat our homes. And of course, at some point on the journey here, around 1712 actually, we had the steam engine, we had deep mining for coal, and we had the Industrial Revolution. And coal then became the dominant form of heating. And of course, we had the Great Smog in 1952 and the Clean Air Act. That probably spelt the demise of coal for heating. And gas then came to the fore. Again, there were a number of things happening. There was the OPEC crisis, and there was also North Sea. And now we have another crisis. So you have periodicity of crises causing change. And the latest one is climate change. And electrification is not new. I mean, I remember when I was a student trying to dry clothes in front of a bar heater and stuff like that, and so on. But heat pumps have been around for a while, but we'll say more about that history in a minute. Now, I have to say, it is somewhat depressing that there seems to be a tsunami of pieces that are really trying to take negative pieces about heat pumps, and it's very bewildering as to why this is. We can all speculate about the motivations. But I think you have to be very skeptical about what you read in the papers, is what I would say, because a lot of it is not very accurate. Now, this looks like a messy slide. I should add that you can get these slides, download it at the end. There'll be a QR code at the end, and I think you'll be able to get it through the website. The point about this is that the history of heating with heat pumps or heat pumps, shall I say, and electrification is very old. I'm just going to point out a few things. Faraday, 1831, electromagnetic induction. We had the first patent for a refrigerator in 1834. We had William Thomson, later Lord Kelvin, proposing heating homes with heat pumps in 1852. And in the 1930s, we had a whole industry being formed out of what we now call HVAC, which is heating, ventilation, and air conditioning. And there's 40,000 HVAC engineers in the UK, and we say we don't have enough engineers. Well, maybe we just need to retrain them to do the heating stuff, and we'll be fine. And then we had Dakin in 1982 inventing the inverter-based heat pumps, which meant that they were more efficient and quieter. So massive things happening. So electrification and heat pumps have a long journey, 200 years of history, and with various things being electrified. The future is smart grids and smart homes, and we just need to get on with it. Okay, so demystifying heat pumps, because they do seem like magic to a lot of people. Another thing that happened in the 19th century is that we finally settled what is heat, because people thought it was a fluid, anyway, people like Boltzmann and Maxwell said, no, it's just a kinetic thing. It's molecules moving around. And the faster they move around, the higher the temperature. And it's only when they stop moving around that you get to a thing called absolute zero, which is minus 273 degrees centigrade or 0 degrees Kelvin. So when we think of minus 10 degrees C, we think that's really cold. But from a molecular perspective, that's 263 degrees Kelvin. There's still a lot of jostling around. There's still a lot of energy. We just need to find a way to harvest that energy. And that's what a heat pump does. So we gather up ambient energy, or some people call it low-grade heat, from the environment, and that can be from the air, the ground, or water. We concentrate it using a heat pump, and then we move it somewhere. And if you're heating a home, you have to move it into the house, either using water, the traditional plumbing or in the States, they love their air ducts in their homes. And actually, the physics involved in a heat pump is something we're all very familiar with. We know that if you're very hot and you mop your brow, it cools it because you've got the evaporation of the water, takes heat away from. We know that if you pump a tire up under pressure, you get a hot end of the pump. This is basic physics, very old physics, and it's the kind of stuff that's going on in a heat pump. Except in a heat pump, we're using a different working medium. So we're using a medium that's typically got a boiling point of minus 50 degrees C, which is much colder than, so for minus 10 degrees C is hot for that liquid. So it can do this trick of evaporating and capturing heat. We can then compress it and then condense it to capture it again, to then move it into the house. And then the working medium can go back around the cycle. And it's various names for this process. Because fridges were the original things that this was invented for, it's called a refrigeration cycle. Professionals call it the vapor compression cycle. I like to call it the heat moving cycle, just to use plain English, because that's what it's doing, heat moving. And we have lots of heat moving devices, heat pumps. We have a fridge, which moves heat from inside the fridge to outside the fridge. We have air conditioners that move heat from inside the building to outside the building. And then we have an air source heat pump that moves heat from outside the building to inside the building. I have a tumble dryer at home that has a heat pump in it. People have cars that have heat pumps in them. They're all over the place. You can't escape them. Right. Now you may say, okay, you've demystified the heat bit, but how is it that this volume of water here requires 3,500 times as much energy to heat it by 1 degree than the same volume of air? So if this is the water coming into my house at 1 meter per second, and I've raised it by 5 degrees, what am I going to do? How am I going to harvest that much of air? Well, the idea is have a bigger pipe. We need a bigger boat, guys. So this has got 350 times the cross-sectional area of that tube. 350 times 10 is 3,500. Problem solved. I just needed this to move at 10 meters per second, and I'm capturing as much energy as I need to put into the house. It's not a mystery. It's not magic. I've just sort of created that picture really to summarize what I've just said as a kind of record for you when you come back to look at it. But that's just basically what I just said, that picture. And if you stand in the front of a heat pump, you'll notice you'll get this cold draft because it's extracting this heat from the air and you're getting the cold air or colder air. Part of what I want to do in this talk is also deal with some of the jargon you'll hear. Now, one of the jargon words you'll hear is efficiency. Now, it's not a new word, and in fact, it applies to everything from a pulley to a car. I don't know if I'm doing something wrong with this mic. Yeah. So we have a machine. You get some useful effort out, but you always get waste heat. So output is input minus waste heat. Efficiency is always output divided by input. And the efficiency is always less than 1, is always less than 100%. So if we take a car, it's actually a lot of waste. And it's about 30% efficient. Now, a heat pump is somewhat different because here we're actually cheating because we're harvesting this energy, adding it to the inputted energy to drive the pump. So the output is the input plus the harvested energy. What's called the coefficient of performance is still the output divided by the input, but the heat pump is always going to have an efficiency that's greater than 1, greater than 100%. And if you average this coefficient of performance over a year, you get another piece of jargon you need to know, which is called the seasonal coefficient of performance, or SCOP. And you'll hear it mentioned a lot. Sorry if I'm being too ambitious here with the so really, a professional heat pump engineer should be able to achieve 3.5. That's 350% efficiency. Electricity in, heat out, heat to the radiators. 1 kilowatt hour of electricity in, harvested 2.5 kilowatt hours of heat from the ambient environment, delivering 3.5 kilowatt hours to your radiators. And there's a little subtext there for the scientists in there that are going to pull me up on something I just said. Flow temperature is another piece of jargon. That's just basically the temperature of the water coming from your heat pump or your gas boiler or whatever. That's the flow temperature. And then it loses heat and heats your rooms, and it comes back cooler than when it went out, and that's called the return. Now, apologise, I'm showing you this slide because it's quite important, but I appreciate that a lot of people don't like graphs. What this graph is showing you is that the performance, this efficiency I was telling you about, is better the lower the flow temperature. But we have plumbers that are used to sort of putting in a gas boiler, setting the flow temperature to a fixed number, maybe 70 degrees, and if you just set a high flow temperature with a heat pump, you're not going to get the best out of it. In fact, the performance improves tremendously the lower you can get it. Now, you can't just keep lowering it because your house may be leaky and you may need to raise it a bit. But basically, you want to try and get as low as you can. So there's a thing called weather compensation. Heat pumps, actually gas boilers can do it, but quite often it isn't set up correctly. But with a heat pump, certainly, it knows the external temperature, it knows what you want to get inside, and it says, how hard do I need to work to achieve the temperature you need? And it will work as hard or as little as it needs. But if you've got to have weather compensation set. So fixed flow temperature is not a good setting. And you want, the lowest flow temperature consistent with your budget, because it might involve spending a bit more on radiators and so forth. So I've produced this. I produced these graphs here. If we take a worst case SCOP and a best case, if you go from worst to best, the cost of installation is going to go up. Maybe you need an extra radiator changed or whatever it is, or change the hot water tank. But from a performance point of view, if you've got a more efficient system, your running costs are going to go down. So what do we do? I mean, if we've got somewhere in the middle maybe, which is a sort of compromise. And what I would say, my recommendation would be, try and make sure you're not paying more with your heat pump on your heating than you were with your old system. So I'll call that the break-even SCOP. And perhaps do a little bit better than that. If money is not no object, but if you really want to have a really great system which with the lowest possible running costs, maybe you invest a bit more to get the lowest possible running costs. And then I would say there's something in between which I would call the pragmatic zone. I've just invented this. This is my jargon, okay, not the industry. So this is where we are. So I think it requires you to be sufficiently well, hopefully this talk will help you with that, but sufficiently well briefed that when someone comes through the door and says, you can have a conversation, you can challenge them. If they say, we need to change all the radiators, say, well, why? Because often that's being too risk averse. Now, why do we need to worry about heating? Well, if you use the parish calculator tool, which is a brilliant piece of thing, you can access it for free. I did it for Wootton. 38% of the territorial household carbon footprint is house, and I think a lot of that is heating. Say 3 tons for the household per year. So it's a significant chunk of the carbon footprint. We're doing a pretty good job with if you like, last year, I think over 50% of the electricity generation came from renewables. So that's going pretty well. But we're still burning this stuff in our homes, and we're still burning it in our cars on our streets. Good news is, these things are so efficient that you don't actually have to build as many wind turbines as you thought you might if you did a naive calculation, which is what happens with a lot of perhaps people with not particularly good motives will sometimes say, oh, you need 7 times the electricity we have today. No, you need something between 2 and 3 times the current electricity capacity to get to that green picture at the bottom. This is a graph I did, which Nestor liked, so that they borrowed it, and it appeared in The Guardian as well. What I did was I plotted the capital cost of different interventions against the carbon saving per year. And on the right, you'll see there's a heat pump with or without the £750, 7,500 grant. The only thing that beats it is, say, loft insulation, which only is saving you 1/10 of the carbon, but it's at less than 1/10 of the cost. So what this is saying is, in terms of bangs for your buck, a heat pump beats pretty much everything significant. And actually, 3 tons saving, as the grid gets greener and greener, you keep saving more without having to do anything. But if you add up all these measures over here, the wall insulation, the MVHR, all the things that you're told by retrofit specialists that you need to do, you can easily blow 30 grand, no problem. At 4 times the cost to achieve the same carbon saving. So I think we need pragmatism here, and we need to be careful about blowing all of your domestic budget on fabric measures before considering a heat pump. So that's what that says there. Again, for the record, when you get to look at these slides. So do I need loads of insulation to make a heat pump work? Well, I was told that before we got ours. Appropriate insulation is a good idea. If you've got a cold bay window, it might be that you've got to do something about it. And it doesn't matter what the heat source is, but it's nothing to do with a heat pump. It's just, if you've got a thin wall and it's -5 outside, you're going to get a cold gradient. Doesn't matter what the heating source is. It's nothing to do with a heat pump. It's the fact that you've got a thin wall next to so I think, again, and insulation work is not without risk. So we had the National Audit Office report came out a few weeks ago, and they looked at a number of measures, but one of them was external wall insulation, and they found that 98% of these things under this eco scheme were substandard, in some cases terrible standard. So it doesn't matter what you do in life. If I want to pay for my granddaughter to have laser surgery, I'm not going to wait for the first person to knock on the door. I'll probably go for someone who's very good with a good record. And it's the same if you're getting wall insulation or heat pump. This is not a special problem for heat pumps, trying to find good people. You just need to know how to find them. And I'll talk about that a bit. And the report was done by Catapult, which showed there's nearly no type of house that cannot take a heat pump, whether in terms of age or type of house. And yet I was told this repeatedly by people, architects, people from councils, retrofit experts, friends very green friends with a small g. Because it had become a mantra, but you do need a good supplier. This is a picture of part of a house, a Georgian property, which I bought with my wife 30 years ago. Those front windows are single glazed. A lot of them are wafer thin. And I was almost shouted at, you cannot heat that with an air source heat pump. Anyway, we do. And we get a SCOP of 3.68. And compared to the old boiler, because that's what you're going to, I think you've got to compare it to, which was 30 years old and creaking. There was no ripping out of a new boiler. We're replacing a creaking old boiler. We're saving money compared with if you kept the old boiler. No problem. No fabric measures above and beyond a little bit of draft proofing on sash windows and loft insulation. I mean, there's a lot of things you can read, and Carbon Brief have a list of 18 what they call myths about heat pumps. I mean, and these are repeated with great confidence by people that don't really know a lot about heat pumps because they've heard it. So it becomes a kind of Chinese whispers thing. And I think you've just got to be very careful to challenge some of these beliefs, if you like. Okay, show me the money. Well, before I show you the money, our electricity grid is not fit for purpose. There are lots of problems with it. Despite the fact that over 50% of our electricity last year was generated by electricity, over 85% of the time, the price of gas was determined by the price of gas, which is determined by international markets. And then you have the other paradoxical thing of wind farms being told to turn off because they're producing too much energy and they can't get it to where it needs to be used. So there's a whole host of problems. I've got a list of them there. That's another talk. That's a 2-hour talk to get to the bottom of that lot. But what I just want to show you is this picture, which shows the uptake of heat pumps versus what's called the spark gap, which is the ratio of electricity to gas. In Sweden, where the spark gap is about 1, so unit price of electricity and gas for the householder is about 1. Uptake is very high. For the UK, which is that little orange dot down in the bottom right, spark gap is quite high. It's over 3.5. Uptake is low. So you might conclude from that, well, we might as well give up. Go home, Richard. Why are you giving this talk? Okay. Well, let's take an example. I'll just run you through some maths. This is basic arithmetic. So imagine we've got a building that on the annual bill for the gas, it says 30,000 kilowatt hours. The unit price is, say, 6p per kilowatt hour, so that's 1,800. I'm ignoring standing charges for the moment, but I'll bring them back in later. But we had an old gas boiler, say, that was 75% efficient. And believe me, for many old gas boilers, that's probably optimistic. So the actual demand of the house, because a lot of it's being wasted, 25% is being wasted, is actually 22,500 kilowatt hours. So the big question is, does this fantastic efficiency of the heat pump trump the spark gap? That's the question. So let's see. Let's suppose we have a heat pump that has 3.5 SCOP. So the amount of electricity needed to power the heat pump is 22,500 divided by 3.5, which is 6,429. Multiply that number by the unit price of electricity, 22, and you end up with 1,414, which is a saving. So when people talk about spark gap, they don't mention the inefficiency of the gas boiler compared to the efficiency. Well, they might pass it, but they don't do this. This doesn't require anything other than basic arithmetic. Health warning, of course, is that the spark gap might change and the SCOP might not be as good as it should be. In the future, with that reformed gas market, it's going to be a cinch. It's going to be a doddle to do this. At the moment, it can be a bit marginal. I redid the calculation with a calculator that I've put in a folder that you can access, so you can play with it for yourselves, this spreadsheet. And I added in the standing charge. And you can see with the different SCOPs, you get different savings. And a break even of about SCOP of 2.9, which frankly, if the heat pump engineer can't beat that they shouldn't be practicing really. But the interesting thing is that if you're looking at carbon savings on this particular house, if you like, is you're getting more than 4 tons of carbon saving, even when you're down at 2.5 SCOP. Again, small print with all the assumptions. That's just so you've got a kind of record. And that's the spreadsheet I put together, which you can use and play with. And I've got instructions of how to use the spreadsheet, so you can play with it. The other thing is changing mindset. So I mentioned about this typical thing of having hot radiators. It's not efficient even for a boiler. You should be trying, even with a boiler, to set to a lower flow temperature as you can. And you don't need radiators at 70 degrees to heat a room to 21 degrees. People seem to accept the fact that you can have underfloor heating where it's 27 degrees on the floor. But if I take that floor and fold it up into, I did this once, as a concertina, so you can actually create a radiator from that floor area. And it fits, it's like that big. But apparently that doesn't work, in people's minds, because they say, no, it's got to be hotter. So it's a strange, we've got ourselves into a psychological thing of tapping the radiator to check the heating's on, but it actually doesn't make any sense. So the flow temperature of 35 to 45 in winter is fine. Actually, I do tours of our house, and what I do is I get people to put that on the radiator. They say, is it on? They say, it doesn't feel on. I put it, we look at your hand, it's saying 27 degrees. The radiator's at 32 degrees. It's not going to feel hot, is it? Now, what does the thermometer say on the other side of the wall? Well, it says 21 degrees. How does that happen? Because you don't need it at 70 degrees. We've somehow got ourselves into this. And it's because we put our heating on for a short time in the morning and then short time in the evening. But if you have it on steady, you do not need it on at 70 degrees. I'm going to try and change the slides with that. And you may need to fatten them. Sorry, that is actually from my studio, and about a third of our radiators need fattening from double panel to triple panel. I was surprised it was only a third. And they do, it's actually more expensive to run a heat pump in the way you run gas boilers, sort of trying to heat and then let it cool down, and then, this roller coaster effect. Slow and steady is better, and it turns out to be cheaper that way as well. And of course, it's got the weather compensation. It's only working as hard. So when you say it's on all the time, it's aware all the time. Do I need to do some work? No. Now, I was asked by the organisers to talk also about other than the domestic situation. So social housing, for example. So I just want to take you through some examples of where heat pumps are used in settings other than, a owner-occupier. So these are flats. One is in London, and they're using this sort of Kenza, what's called an ambient loop. So what it does, it uses boreholes to bring up water which is at, say, 12 degrees, which is actually quite good because it's not losing a lot of heat when it's being piped around. And then in each flat, you then have a sort of shoebox heat pump, which then boosts it to a temperature to heat the flat. And it can also be used in reverse, in fact. The other one is from social housing in Glasgow, where they replaced a large oil-fired boiler with a large air source heat pump. And again, so you can either have large centralized units, or you can have this idea of using a distributed model. And there's lots of permutations on that. I only learnt this about 6 weeks ago, but my local surgery in Nailsworth actually is heated with a heat pump. Well, it has been for the last 2.5 years. I didn't know that. I knew they had solar, because you can see the solar when you walk down there, but it actually has a heat pump. And rather than one big one, they got 3 smaller ones, which actually helped it integrate with the grid more. But you'll often find this. There's places that are heated by heat pumps you didn't realise. Amberley Church uses what's called air-to-air. So in this case, you have what's called a split system. So you have the heat pump, and then it's passing this refrigerant through very narrow tubes inside to convectors that then blow hot air out to heat spaces. So it's very good for spaces like this, rather than having radiators around. And then this community space in Bristol, they have solar and they have ground source heat pump, and they use this interseasonal heat transfer. So in summer, they will cool the building using heat pump. So I think they must be using air-to-air for heating the space and cooling the space. And then they stick heat back in the ground to help recharge the ground. Obviously, the sun is doing most of that, a lot of that, but it just gives it an extra boost, and it increases the performance of the system even more than it is. So that's a very interesting, innovative model. And then you have zero bills homes. So Octopus are teaming with lots of builders to build new homes where there'll be zero bills. How can they do that? Well, because they're generating electricity, and there's a quid pro quo, and they have batteries, and sometimes the quid pro quo is, oh, we need a bit of your energy, please, to help balance the grid or whatever. So it'll all be done by some brain out there. It's called Kraken. Believe it or not. And the government is supposed to be coming out with a future home standard that seems to be taking forever to appear, but hopefully it's going to have some of this innovative thing. I mean, too often they've been a bit scared to be brave with some of these things and have sort of soft-pedaled, shall we say. So we're still building homes with gas pipes going in them, which is madness. But, we could be doing something a lot better. And then heat networks. And this is really, in a way, not a new idea. In Denmark and places like that, they certainly you'd have these large bioenergy things pumping hot water around. But this is more sophisticated. It's using heat pumps, and companies like Rendesco are doing the whole shebangle. They're doing the design, the financing, the operating model of this thing, so that the flat owner or house owner then is only really paying for heat as a service in the same way you pay your water bill or your electricity bill. It just simplifies the whole thing for everybody. So you don't have to be an expert about heat pumps any more than you have to be a heat pump about cars when you drive a car. Why? Right, final thoughts. I think I'm still okay. So the future is clean and cheap power, and it's not that expensive. It costs money to do it, but the Climate Change Committee reckons on average between now and the period of building out this infrastructure, it's something like 0.2% of GDP. It peaks at around 60 billion a year, but 90% of that is private sector, so it's 6 billion, which is less than we spend on fizzy drinks, which is about 10 billion a year. And the sun is free. Once you've built this stuff, there's no cost. I don't have to buy any gas. I don't have to dig the ground up to get the energy. The sun is delivering it for free for at least a few billion years. HeatGeek, look at HeatGeek. They're really making waves. They're challenging some of the kind of geekyism that has often surrounded heat pumps. They want to try and simplify it, and they've come out with an offer now, which is called Zero Disrupt, because they have a contention that too often you'll get suppliers coming in being a bit conservative. They put in all these parameters into a massive spreadsheet or calculator, and one of those would be air changes per hour. How leaky is your house? And it might be that it's only 1.5 times an hour, but they're not sure. Oh, they're going to leave windows open. Let's put in 2.5. And you add and you compound all these factors, and suddenly you find you're going to have a bigger heat pump. You're going to have more radiator changes. You're going to have higher cost. So it's worth getting more than one quote. That's for sure. And it's worth possibly considering them. I'm not recommending them. I'm just saying consider them. And by the way, I'll have a link to some help guide actually in terms of selecting. But I like the idea of a value-based journey for customers. Customers who are sufficiently informed to ask, challenging questions of the supplier, saying, well, why do you want to change all my radiators? I've got mostly double panel. Flexibility is this whole idea of now, instead of these large generators around the country and these big pipes going to smaller pipes, we have this network of generation, sometimes on your own house. We have network of storage of different sizes and scales, and we have a lot of digitization so that your car will be charged sometime between when you go to bed and when you get up in the morning. And maybe it's helping to put energy back to the grid when needed, but you get what you want when you need it. And this flexibility is going to be a game changer, because you don't have to build so much infrastructure if you introduce this flexibility. Right, I'm going to end with more history, but it's a historian of the future. I'm thinking of a historian in 500 years' time, looking back to that wood phase, and then being in this electrification phase, and then looking at this blip in the middle, which was the 200 years when we thought, well, we basically had this poison chalice, which is the fossil fuel area, where we've taken fossil fuels which are 300 million years old and decided to burn them in a period of 200 years, and even when we knew that was causing damage. I'm borrowing Amitav Ghosh's words, the great derangement. This will be seen as by future historians, I'm convinced. And electrification, as the great, unfortunately, sadly departed David Mackay said in his brilliant book, electrification is future-proofing. Once you've built the infrastructure, if you decide sometime in the future there's fusion energy, just plug it in, okay? And everything still works. It's a very efficient way of moving energy around, and because the end use is very efficient as well, it means you don't need to build so much capacity and generation once you've electrified everything. So it ticks so many boxes. And we have the solutions. It's not about, oh gosh, we've got to wait for... No, we've got them. We've got all the technology we need now to decarbonize those big beasts of transport and heating and so forth. So I've got some takeaways here, which are some websites, useful websites, a few books, including this one from Heat Geek, which is this is really for plumbers and engineers who want to look at good practice, the Heat Geek way. And just a little plug, I gave a talk last year, not here, but about how do you make the grid green, and what's that involve in terms of storage, long-term storage, et cetera, et cetera. So that talk is available, and there's a link to it in this pack. The other thing I've done is I've created getting a heat pump checklist. So I've got a checklist, and at the end of that, it's also got tips on when you're selecting a supplier. And a lot of this is soft stuff about gut and so forth, not just technical stuff. But that QR code I'll leave up. If you just point, I think it'll become available, the link, through the Wootton Area CAN website. But if you want to grab it now, you can, during the drinks break, just point your phone at it, and that will send you to a folder in Dropbox. And there's 2 documents in there. There's a PDF of this presentation, and there's a Excel spreadsheet for that calculator. So I put a shift in for you guys. Okay.
What about the size of the unit needs to go on the outside of the house?
The way they do it, or the way they should do it, is they do a heat loss calculation for every room in the house to reach its target temperature. So maybe for the sitting rooms 21, for bedrooms 18. These are the MCS standards. For bathrooms 22 degrees. You do all of those, you add them up, and you get a total. And then you look at that total for the coldest day of the year, the nominal coldest day of the year. Again, MCS will say this is the kind of standard you need to be doing. I think for us it's sort of -3 degrees. If it was in Scotland, it would be -7 or something. So it varies according to where you are in the country. And based on that, you end up with the power output, the heat power output of the heat pump. Now, physically how big it is will vary a little bit on the design of it. But the important thing is what the heat. So when someone says 11 kilowatt heat pump, let's take 12. If it was a 12 kilowatt heat pump, that's the heat going out. The electricity to power it will be less than a third of that, so less than 4 kilowatts. But there's a process they need to go through to get the size of the heat pump. And the only thing I was saying earlier was that sometimes people can be over-conservative or risk-averse, particularly if they're inexperienced, and they add on a margin here and a margin there and a margin there, and those all add up to being, twice as big as what Heatkeep would recommend, for example. Were you thinking about the physical size of it?
Yes.
Well, the physical size of an 11 kilowatt heat pump I've got is something like that, about that high,
And how deep?
and about that deep. And these are called monoblocks because they've got all the gubbins inside them. Yeah. And they should be mounted on a flat surface. They should have vibration things on them, and then they shouldn't be any more noisy than your, I mean, they're not. They shouldn't be noisy if they're set up right. Yeah. Yeah.
In order to stop my wife's feet getting cold, we've had some advise us that our kitchen should have underfloor heating with some electric mats under the floor, because that would avoid them having to dig down to put the pipes in for the water from the heat pump. And from what you've told me, that means I missed that magical 350% efficiency and will be really expensive. Is that correct?
Yeah, you're paying 3.5 times as much for your electricity than you need to.
Can you tell my wife that?
I nearly have to shout because she's not here.
You can just sit her down with a hot chocolate, and you can just run through the presentation.
I'll just send her the QR.
Yeah.
Okay. Well, I was just going to say, to avoid the complexity of compatibility with heating pipes from an existing system, you could always fit air conditioning, and we're susceptible to heat waves. It's becoming more prominent in summer, so you can heat and cool with that system just by blowing warm air around in the house.
Yeah. I mean, it's really to use what was called air-to-air, and air-to-air heat pump system for a house, which is very common in the US.
You can heat and cool then. So,
Yeah.
you've got the advantage of that.
Yeah, I think there's probably different schools of thought, sometimes quite passionate about in pros and cons of this. I mean, it does mean, say, for a larger house, if a room like this, no brainer. But if you've got a room that has, say, 7 rooms in it, then what are you going to do? Are you going to have
up to 5 internal units?
Yeah, no, I know, but you then have to start running what's called F-gas pipes. These refrigerant pipes around, and so on. It might be the right solution. Some people go for that. We have I suppose a plumbing culture, a radiator culture. It's not necessarily the right thing. I think for new builds, it's a whole different story. I think mainly, I think people are going for underfloor heating. So the issue of distributing heat using air is not. Some people find it comfortable. Some people don't find it comfortable. In terms of, some people say that radiators or underfloor heating is a more comfortable heat. But I think that a lot of these things are quite subjective, shall we say. So I think you're right, and I think the cooling aspect of this is a very important point that you're making. I would add, though, that in terms of build, architects are now thinking and saying we should be doing things that perhaps they did in the Mediterranean. They've been doing in the Mediterranean for years, which is having intelligent shading. For example, so and I love the idea of just having a row of silver birches that have leaves on it with cuts, so the canopy, you can look under it, and then in winter the leaves fall off, and etc. So you don't get too much solar gain, what's called solar gain in the summer, but you get shade in summer, but you get open sky. So there's lots of creative ways that architects and garden designers can solve some of the overheating issues. But technology definitely has a role. But I'm not giving you a simple answer, because I don't think there is a simple answer. I don't think it's a question of saying everyone go for air-to-air heat pumps, because I'm not sure that is the answer, to be honest. Yeah.
I've got two questions really. One is about, well, going back to the wife question. My wife wants to put laundry over the radiators, and now she's complaining because the radiator's running at 38 degrees. She's not drying her clothing off on the radiators. So how can I appease her and get the radiators a little bit hotter in our heat pump? And also, are there any new sort of exciting changes coming out to the basic heat pump? I know we've had the new coolant, which has made or refrigeration unit, which has made a great difference to the efficiency of it. But is there anything else coming out that we should be looking forward to?
We don't have a problem drying our stuff. We have a clothes horse.
Yeah, that's what I was going to say, because with the ambient temperature in the room, everything dries.
Yeah, it dries. And frankly, you stick it on 70 degrees, it's going to come out crisp, rather than nice, soft and gentle. So I'm not convinced that putting your clothing on a 70-degree radiator is a good way to dry the clothes. So I think slow and gentle. And then on the innovations thing, well, I think one of the most important innovations I think you alluded to was we were using this, which has a global warming potential of 3,500. It's interesting, there's a whole talk about the Montreal Protocol I could give, but where the 87, because of the ozone layer, they got rid of fluoride and things because they were eating up ozone in that thing. And they were replacing the stuff which didn't eat up the ozone layer, it was really pants when it came to global warming. So now they're wanting to replace these. A lot of R32, as it's called, is this molecule, which is in our heat pump, which is better, but it's still at 675 global warming potential. Europeans use this, which is propane. Yes, it's combustible, but you're only talking about 300 grams in your heat pump, and we're quite happy to drive our grandchildren around with 60 litres of petrol in them and have a pipe going into our kitchen pouring methane in there, which we burn and inhale the fumes. And we're worried about 300 grams of this in a heat pump, which is in a closed monoblock. So I think this is a way to go, because it has a global warming potential of 3. So that's 1,000 times better than the stuff we're using for.
What's its efficiency like compared to R22? Where it is?
Yeah. So I think in terms of the basic physics and mechanics of you might be able to build a better compressor or things like that. But I think there's so many millions of these things around that they've really tuned this. I mean, it's not like it's new technology. I mean, you believe from the press that this is new stuff, but it really isn't. So as I said, Dakin invented the inverter-based heat pump in '82, and this stuff's been going for a long time. So I'm not convinced there's some magical new mechanics involved, but I think some of the materials, yes.
Point of clarification, really. You've mentioned Heat Geek,
Yeah.
and the chap over here is using. I've been following Adam at Heat Geek for some time, and I believe he talks a lot of sense, and whatever he comes up with sort of resonates with me. I believe he's approaching the whole transition to electrification via heat pumps in the right way. But I'm a bit confused that I didn't think he actually provided an installation service. He was training people to provide the right advice and the right installation, and therefore to go through Heat Geek, it was more putting you in contact with a trained installer. Is that correct?
Yeah, so the question is, what does Heat Geek provide? I think that is my short version. And yeah, it's training, but they would say they provide a community, because I had an exchange with them about this. I said, well, what if I'm an SME, a small, medium-sized company that's already got a bit of a name for myself doing heat pumps, and I quite like your zero disrupt thing, but actually I'm pretty low disrupt anyway already, but maybe I want to wear your badge doing stuff, can I do that? He said, yeah. But so I would worry about going to a sole trader because I'm worried about support. But what they say is they will underwrite people doing.
Yeah.
And just to extend the answer a little bit, what they've done is they've taken hundreds, and I'm sounding like a salesman for Heat Geek, but I'm really not. But they've taken hundreds of installations and mapped them out, and they've used cameras to try and assess heat loss, and they've churned it through some AI machine to make it quicker and easier to avoid making just hunched guesses, you know, and try to get a better estimate. And then to say if they get it wrong, they will fix it. So they're saying they will if people follow, if they train up and say they're going to follow this process. And what they will do is monitor the installation as it's going through, they'll monitor the performance. And if they can see it's going south, they will know. Previously they said you should be aiming for 4 to 5, but that then would be on the right hand, that graph I produced, that would be on the right side, the right hand side of that graph which I...
But as you say, we don't need to be chasing efficiency, we just need to get heat pumps installed.
Well, it depends. It depends. If you've got the money to get a higher efficiency and you're worried about another war in the Middle East, you might say, well, I'm just going to go for it.
That was your graph, is it?
Yeah.
No, this one.
Yeah.
So do I go for the pragmatic zone, or have I got a few spare pennies and what the hell, I'm going to replace all my radiators and get the best possible thing, which might be overkill.
Yeah.
But he's worried about people uptake, and he's worried about people not being able to afford it. So he's saying, well, we need to find a way to minimise disruption. And
to maximise
to make it
uptake.
as affordable as possible.
Yeah.
Even to the point in some cases saying it's free. Because with the 7,500 grant, they can actually get it down to that level. Right, sorry. That's a long
I was just going to mention another way of saving considerably on the purchase of electricity is to install solar and storage batteries, and that will run your heat pump. This is all technologies I use.
Yeah.
I actually make money out of energy because I'm tied in with a feed-in tariff.
Yeah.
So
the point, that the observation, which is a good one, is that if you've got solar and battery, you've got and that's why Octopus are offering these zero bills homes, because they can play with these things.
Yeah.
Now people will say, well, you're getting most solar in summer, whereas the peak heat demand is in winter.
yeah.
But what I would say is you've got the shoulder months, you've got spring and autumn, where you still need quite a lot of heat,
Yeah.
and you've still got quite a lot of sun. So actually, when you look at it, it still works over the 24 months.
Battery storage at night as well.
Yeah, absolutely. So I think, and that's why these zero bills homes include these three elements: the solar, heat pump, and battery. Yeah. And good. Oh, the fourth one is good installation as well.
Yes.
You haven't mentioned anything about these rather imaginative electricity tariffs that are being offered to perhaps potentially keep your energy bills down, especially if you're running heat pumps in combination with electric vehicles.
Yeah, so I mean, I think there are some some great tariffs out there, but you need to make sure that you can get out of them if you need to. You need to understand, what the implications are of those tariffs and whether they include everything. Because there may be some aspects that aren't actually included, but there may be the small print may say that certain things like their fixed costs, if they go up, then those are not protected by the tariff. So, it is a question of, maybe I'll do a blog about that, because I was asked to do a talk to GP practices in Gloucestershire, and it was about tariffs, so I dug in deep on there, and it's surprising actually how complicated it is. But I know someone who's got themselves an EV, and they still don't have solar, but even though they've got an EV, they've got this intelligent tariff, which means they're actually paying less in electricity now they've got the EV, which is bizarre, even though they don't have solar yet. I don't know how that works.
Would a heat pump affect sort of like the moisture levels in the house compared to a gas boiler? Is there an advantage in either, or does it depend on the fabric of the house?
Well, moisture, there's a basic law of physics that says that for every degree, 1 degree rise in temperature means that the air can hold 7% more water. So there's always a relationship between the temperature, but that's irrespective of the heat source. And as long as your gas boiler is not pumping its output into the house,
Yeah.
you shouldn't be getting the moisture of combustion coming into the house.
Yeah.
So I'm not sure whether there is an issue with ventilation. The more, and this is again where this whole fabric thing becomes a little bit more complicated, because if you start blocking up an old house
Yeah.
that used to breathe and no longer breathes, suddenly you find moisture spots appearing. And the retrofit people say, oh yeah, but you should have done this and you should have done that, and we need to put MVHR in there, and that's when you get to your 30 to 50 grand.
Yeah.
Or if you're one of the victims of one of these poor things, you end up with an unsellable house. You know, because there are some really horrific things can happen, like putting foam inside the loft of a listed house or something like that. You know, there are some really disastrous things that people can do, which is why, you know, having some good advice. Where we're not very good at buying advice in the UK. We seem to think, oh no, that's an overhead, we shouldn't do it. Let's just get on and do it. But you know, if you can get someone skilled in, that can save you money in the end. So getting a couple of quotes, you have to pay. You know, maybe you have to pay. I don't know what are you paying for the quote.
375.
375. It sounds like a lot of money, but if down the road it turns out you need 20 grand to fix a mess up, suddenly that starts sounding cheap. Yeah. So get advice. Good advice. Yeah.
Yeah, I was just going to ask, given your minimum disruption idea, we have a conventional 30-year-old gas boiler, wet system. Could you not size the heat pump based on your existing boiler, have it fitted, see how it works, and then if you've got a room that's not getting warmer, then fit a larger radiator?
It's a great idea.
Is it too simple?
No, it's not too simple, and people have done that. You know, people have said, look, instead of running a gas boiler like, if we can run it slow and steady, so let's go slow and steady, let's set it to, say, instead of 70, is it on 70 at the moment? Or?
It probably is. I mean, it's only got the low and high. We have it on low, and we tend to run it.
So maybe you don't have the controls on there. If you go to www.theheatinghub.co.uk, they do lots of stuff around boilers and stuff and things you can do to tune current boilers. So if people want to just don't feel they're ready for a heat pump, but they just want to lower their heating bills, that's a great place to go. Some really practical advice. But yeah, you're right. One way to test whether or not is just test using a flow, keeping it on longer at a lower flow temperature. So we have ours on 24/7, 365. It's set back to, we have one thermostat. So again, people get very clever. Oh yeah, but if you have all these systems and you have these controls here and there. No, keep it simple. So we have one thermostat. It's in the sitting room, set to 21, and set back to 18 between 10:30 and 6:30. Nothing else. And then if all the other sizings, if the sizings are correct in all the other rooms, they will reach their target temperature.
We've got a 1991 detached house. We don't want to do loads and loads of stuff. We're thinking about triple glazing, but I say I'm more worried about the boiler packing up. And I'm thinking, do I want to replace it with a more efficient gas boiler, or do I want a heat pump?
So being a bit of a geek, I looked at the marginal cost of, and I can't put double glazing on the front of the house, but on the back we've got some areas where I could put in where my studio is, where I could put new sash windows and new windows, and I looked at double versus triple. I was like, oh, triple. I looked at the cost performance of it and the U values and so forth, did some maths on it, and it really wasn't worth it, you know, to go that extra mile. Now, maybe for a new house it is, and if we seem to want to build these houses now that have walls of glass sort of facing out toward the sun, and then wondering when we cook in summer. I mean, it's just crazy, but anyway. I mean, you look at the Europeans and they have these narrow streets with tall buildings, and yeah. Let's learn from people who know how to deal with that stuff, but we seem to not want to learn sometimes in that way. But I would say it needs to be, put everything on the table and look at the relative costs and benefits. And then what I say is, if you think, oh, I want to do some fabric first, if it ends up being fabric only, I think that's a bad choice. And if it's someone from the Passive House Trust that says, banging on about they want you get you down to 25 kilowatt hours per square metre per year, which is their target for retrofit, when the average for the UK is 133, and on our listed building I managed to get down to, well, it's about 116, something like that. So it's something like 4 times their target or more, 5 times their target. We're never going to get down to there, and it would be madness to try. So yes, comfort, there may be comfort. That bay window, do something about the bay window, because Granny likes to sit there, or Grandad does. And maybe you need to do something there, but so there may be particular points where you need to do some interventions, but a wholehearted, let's just go gangbusters and we're going to throw everything at it, I think it's a very risky strategy, and it worries me that some politicians love talking about insulation because they feel comfortable, but because it's been made so toxic, you know, they don't talk about heat pumps, or they say, oh yeah later, and it disappoints me that some politicians I really respect say, oh yeah, no, you need to do deep retrofit. They're still using this language, and it's not true.